Hello everyone, we are going to start solid state chemistry. In today's lecture 1, our subtopic are unit cell, space lattices, crystal systems and Bravais lattices. So let's begin with unit cell. We all have idea about crystalline solid substances. Crystalline solid substances have a particular geometrical shape, and if it is broken into smaller pieces, that particular geometrical shape is repeated, and this way, when the smallest part is obtained which cannot be further broken, that smallest part is known as the unit cell. That means it is actually the smallest building unit of a crystal. So the smallest building unit of crystal is called the unit cell. It is defined at, let's see what about its definition. So the definition is the smallest group of symmetrically aligned atoms which can be repeated in an array to make up the entire crystal is called a unit cell. So this is the definition of a unit cell. What is the definition? The smallest group of symmetrically aligned atoms. That means the arrangement, array or the arrangement should be symmetrical. Okay, there shouldn't be any kind of difference. Okay, so every part should have repeatedly the same arrangement. Okay, so which can be repeated in an array, that means in an arrangement to make up the entire crystals. So throughout the crystal the same geometrical shape would be repeated. So that is known as the smallest, and that is known as the unit cell. This unit cell is actually the smallest building unit of a crystal. Now let's define lattice point. Lattice point, actually for every crystal they are made up of ionic solids, or they are made up of covalent solids. Suppose glucose crystals or sucrose crystals, sugar, isn't it? So those are covalent solids. Metals, those are the solids which are made up of only cations, and in between there are huge sea of electrons. Or in case of ionic substances such as sodium chloride, potassium chloride, calcium sulfate, copper sulfate, etc. In those cases they are made up of ionic substances such as both cation and anions. But the common in all of these are they are made up of nuclei. That means they have some nucleus, and that particular point where the nucleus is existing is known as the lattice point. And according to the terminology of solid state chemistry, they are known as sometimes motifs, spheres or a point. They are definitely atoms or ions. For covalent substance they are atoms, for ionic substances they are ions, but they are also called the motifs, spheres or simply a point. Okay, so let's see, each atomic nucleus in a crystal lattice is a lattice point. The atomic nucleus may be the nucleus of a metallic ion, anion or cation of an ionic solid, or that of a covalently bonded atom. Therefore, the lattice points are sometimes termed as the atoms or ions. The other terminologies of lattice point are motif, sphere or simply a point. Now, if these lattice points are distributed in a particular way, then we can distribute them in 4 ways, and this distribution of the solid crystals are known as the space lattices. Okay, so this way we can get 4 types of distribution of the lattice points. This they are forming the space lattices, and these space lattices are the primitive face-centered cube, body-centered cubes and C-face-centered cubes. So when a number of unit cells combine in space to form a regular structure, it is called a space lattice. Okay, so there are 4 types of space lattices, and these 4 space lattices, primitive or simple, which is symbolized as P. This is the picture of primitive. Okay, this is face centered, this is the symbol F, this is the picture of face centered. Body centered, This is the picture of body centered, which is symbolized as I. And finally, C-face centered or base centered. This is the picture of C-face centered or base centered, and it is symbolized as C. Now let's describe them. What about their descriptions? In the primitive, 8 lattice points in 8 corners. That means this is the geometrical shape which has 8 corners, and all the 8 corners are occupied by the lattice point. So this is primitive, and no other part of this geometrical shape is occupied by any other lattice point. So this is known as simple. If it is cubic, then it is simple cubic, or it is known as the primitive, symbolized as P. Now, if along with the 8 corners, the 6 lattice points in the center of 6 faces, then it is face centered. If it is cube, it is face centered cubic, or in short, it is known as FCC. For I, that is for body centered cube, 8 lattice points in 8 corners and 1 lattice point at the middle of the 6 faces. Middle of the 6 face means it's in its body center. Okay, if you draw a straight line from the center to all the vertices. Vertices means the plural of vertex. Vertex means the corner. Okay, then all the lines have the same distance, same length. So this is the body center. That means that this is the center of gravity of the whole system. Okay, and if this point is occupied by some nucleus, then it is known as the body centered. If it is cubic, then it is body centered cubic, or in short BCC, symbolized as I. Now if their base centers are occupied at their middle points by some lattice points, then it is base centered or C-face centered. Okay, so atoms in the center of bases of the unit cell along with its 8 occupied vertices. So that's all about the 4 types of space lattices. This is one kind of classification of the unit cells. There is another kind of classification of the unit cells which is according to their geometrical shapes. But in order to learn about their geometrical shapes, we have to have some idea about cell parameters. So what is cell parameters? Cell parameters are nothing but their lengths and angles. Okay, the lengths of the principal axis or the edges of the unit cell, and the angles between them are cell parameters. The other terminologies of cell parameters are lattice constants and lattice parameters. That means these cell parameters are also known as lattice constants and lattice parameters. Okay, and how they are symbolized? They are symbolized as A, B, C, small lettered, and alpha, beta, gamma, small lettered. Now what about A, B and C? Now you will count one thing, that the X, Y and Z axis in crystallography, solid state chemistry, the X, Y and Z axis as A, B and C axis respectively. Okay, now along the X axis the edge length is A. That means along the A axis the edge length is A, along the B axis the edge length is B, and along the C axis the edge length is C. Now the angles are denoted angles made by the any two of the axes are alpha, beta and gamma. Okay, any two of the axis is actually wrong term, any two of the edges. Okay, so at the angles made by any two of the edges are the angles between them, which are denoted as alpha, beta and gamma. We shall elaborate this. Here is the elaboration. Okay, here is the x-axis, which is known as the a-axis according to our X-ray crystallography terminology. This is the y-axis, denoted as the b-axis, and this is the z-axis, is actually the c-axis. So look, along the x-axis the edge length is A, along the b-axis this edge length, that means the distance between these 2 points is B, and this is C. Okay, and the angles, any angle between two, here I am taking A and C is as alpha, B and C as beta, and A and B as gamma. You can also take the angle the angle between A and B as alpha, the angle between B and C as beta, and the angle between A and C as gamma, whatever. So this is actually up to you. Okay, whatever you decide, you can take them. But the fact is that there are only one A, or only one B, or only one C, or there is only one alpha, one beta, one gamma. No, the answer is no. The total number of A is 4, total number of B is 4, total number of C is 4. There are 12 edges, and these 12 edges are described as only 3 cell parameters, A, B and C. That means A means it is representing 4 axes, 4 edges. Which 4 edges? Any 2 point connected 2 points, the connectivity which is parallel to the A axis. That means not only these 2 points, but also look the movement of the laser point, these 2 points also, because the connection of these 2 points is parallel to the A axis. Look at the movement here. The connection between these 2 lattice points is parallel to the A axis, and finally connection between these 2 points, connecting line between these 2 points is parallel to the A axis. So these 4 lines, these 4 edges are actually A. Similarly, the other lines which are parallel to this B, that means this is one, here to here is another B, here to here is third B, and here to here is the fourth B. That means with the lines, the edges which are parallel are actually have the same length. Okay, so you will get 3 set of 12 edges. There are 12 edges, but they are in 3 sets. Okay, each set are having the same length. Similarly, there are overall 3 into 8 vertices. That means 24 angles. In each vertex there are 3 angles, so there are overall 8 vertices. So there should be 8 into 3, 24 angles, but they are only described by 3 parameters which are alpha, beta and gamma. So how it is possible? Look here, there are 4 alphas, 4 betas and 4 gammas. So 12 and 4 180 minus alpha, 4 180 minus beta and 4 180 minus gamma. So there are also 12. Overall there are 24 angles. How? This angle, suppose between A and C is alpha. Now there are 4 faces which are parallel to this face. Okay, there are 4 faces which are parallel, actually not parallel, but what I say, actually in terms of this face. Suppose this face is perpendicular to this B axis. This face, look the movement of the laser point, here to here to here to here to here. Okay, this face is parallel to this face. Now look the movement once again, here, here and here. Okay, so out of these 6 faces we have got 2 opposite faces. Now each face has 4 angles. If this angle is alpha, then its opposite angle, this angle, is also same, because this is a rhombus. This is, if not rhombus, this is a parallelogram. Okay, in general this is a parallelogram. Now if the edges are same, then it is a rhombus. If it is 90 degree, then it's a square. If it is a 90 degree but edges are not same, that is it's a rectangle. Okay, so it depends. Now in general, all the parallelograms, that means all these structures such as rhombus, square, rectangles, all are parallelograms. Okay, so let us use the term parallelogram. So this angle is alpha, then its opposite angle is equal, so this is also alpha, and its adjacent angle, this angle is 180 minus alpha, and this adjacent angle is also 180 minus alpha. Similarly, this angle is alpha, this angle is alpha, this angle is 180 minus alpha, and finally this angle is 180 minus alpha. Okay, so we have already got 8 angles. Similarly, the other 8 plus 8, that is overall 24 angles, can also be described by beta and gamma respectively. So these are the cell parameters. Now according to these cell parameters, there are total 7 crystal systems. But before 7 crystal systems, we should have the idea about the basic regular figures or the subunits. Okay, see what is here. Suppose this is a triangle, and with this triangle you can make these 2 structures also. Okay, this structure does not have any similarity with this structure, but the basic unit is the triangle. Now look at the square. With the square you can make a big square, or you can make a rectangle also. Okay, so the building block or the basic subunit, this is the building block, the equilateral triangle. This is the building block, the square. This is also known as the basic subunit. Okay, so these 2 are the building blocks. The building block or the basic subunits are triangles and squares. Here in this example particularly. Okay, but here they have formed total 4 structures. This triangle has formed a big triangle, big equilateral triangle, along with a hexagon, equilateral hexagon, and this square has formed a big square and a rectangle. Okay, so they have formed overall 4 different structures. Now in crystallography, these building blocks are called the crystal systems. Okay, so these are known as the crystal systems, and there exists 7 such crystal systems which are known as the 7 crystal systems. So let's start 7 crystal systems. Inspection of a wide variety of crystals leads to the, here the A should be omitted, this is wrong English, variety of crystals, it should be variety of crystals, leads to the conclusion that all can be built up only from 7 basic regular figures or subunits. That means here the basic unit, basic subunit, the basic subunit can be of 7 types in our crystallography, or the crystallography of the solid substances which are available in this planet, known as the 7 crystal systems and defined as. So what is the definition of the 7 crystal system? Let me recap this part once again to make it clear. These are the crystal structures, these are the different shapes, okay, made by the basic subunits. That actually we are going to classify these basic subunits. This is a triangle, this is one subunit, this is a square, this is another subunit. So in crystallography there are 7 types of basic subunits. Okay, these are known as the 7 crystal systems. So what is its definition? Its definition is a unit cell in the 3-dimensional lattice is characterized by the unit cell parameters. Unit cell parameters, just we have learned that these are the edge lengths and angles. So that is why cell parameter term we have learned earlier. This is required here. Okay, from these parameters a total of 7 parallelepiped shaped crystal lattices. As I have said, the solid form of a parallelogram is called parallelepiped. That means each face is a parallelogram, and now it may be a cuboid, it may be a cube, or it may be a rhombohedron. Okay, lattice can be constructed which are known as the 7 crystal systems. I repeat, a unit cell is the 3-dimensional lattice, in the 3-dimensional lattice characterized by the unit cell parameters. Okay, from these parameters a total of 7 parallelepiped shaped crystal lattices can be constructed which are known as the 7 crystal systems. So the basic subunits are of 7 types, and these are cubic system, tetragonal system, orthorhombic system. In the cubic system, A equals to B equals to C, alpha equals to beta equals to gamma equals to 90 degrees. This is the cubic system. In tetragonal, A equals to B but not equals to C, whereas alpha equals to beta equals to gamma equals to 90 degrees. Remember the box of a toothpaste. This is a tetragonal system. Okay. Orthorhombic, A not equals to B not equals to B, whereas alpha, beta, gamma all are 90 degrees. Remember a matchbox or a book. These are all orthorhombic systems, or simply a room. Okay, these are all orthorhombic systems. So we have got 3, and the remaining 4 are rhombohedral, hexagonal, monoclinic, and triclinic. Rhombohedral is actually its face is a rhombus. Okay, and its 3D form is rhombohedral, and this is A equals to B equals to C, and the angles, none of them are 90 degree. Okay, but angles are equals. All the 3 angles are equal, but none of them are 90 degree. If it would have become 90 degree, it would become a cube, isn't it? In the hexagonal, it is 2 edges are same, but the third one is different, and 2 angles are right angles, but the third angle is particularly 120 degree. So why it is named hexagon? Actually, if you combine 3 units, you will get a hexagonal surface in the top and the bottom, in the bases. Okay, and in the lateral parts you will get definitely a rectangle, but in the base surfaces, that is C face centers, you will get hexagons. Just try to combine them imaginarily, you will find that you are getting a hexagon. Okay. Monoclinic is very complicated. Alpha A not equals to B not equals to C, alpha equals to beta equals to 90 degree but not equals to gamma, or alpha equals to gamma equals to 90 degree not equal to beta. As I've said, alpha, beta, gamma, you can just shuffle them. Okay, any 2 are 90 degree and the third one is not 90 degree. And triclinic is very easy. None of them are equal, not 90 degree. Okay. So these are about the 7 crystal systems. Now move on to the 14 Bravais lattices. Actually the spelling is Bravais, but its pronunciation is Bravais. Okay. So, and now you combine 4 types of space lattices and 7 types of crystal systems. So you should get 28 combinations, isn't it? Now out of this, in the universe, only 14 are available and 14 are not available. Okay. So when 7 crystal systems are combined with 4 space lattices, they should yield 7 into 4, that is 28 types of combinations. Out of these 28 possibilities, only 14 are naturally possible, that are known as the Bravais lattices. So what is the definition of Bravais lattice? Let's check. The definition of Bravais lattice is: the crystal lattices can be classified by their translational and rotational symmetry. In 3-dimensional crystals, these symmetry operations yield 14 distinct lattice types, which are called Bravais lattices. So from their symmetry elements, we can distribute them into 14 different types, which are known as the Bravais lattices. Okay. Now let's see which is available and which is not available. Here in the first column, the crystal systems, and in the second column, the available space lattices, which are actually the Bravais lattices. Okay, so cubic systems, in the cubic system, the base centered cube is not available. Only the primitive, body centered and face centered, that means P, I and F are available. Here are the examples. Tetragonal, only the primitive and I, body centered, are available. So simple tetragonal and simple body centered Bravais lattice. Only the orthorhombic is the only one system, the only system where all the 4 space lattices are available. Okay. So potassium nitrate, barium sulfate, magnesium sulfate, sulfurate or topaz, all these have the orthorhombic structure, and also the sulfur, which we call the rhombic sulfur, is actually the orthorhombic sulfur. Okay, the rhombic name comes from this name, orthorhombic. We know there are 2 types of sulfurs, orthorhombic sulfur and monoclinic sulfur. The term monoclinic you have learnt right now, and the term rhombic is actually the orthorhombic sulfur. Okay, and this is the only crystal system which possesses all the 4 space lattices. and no other system are having 4 space lattices. Monoclinic are missing F and C. Triclinic missing all except P, and rhombohedral, this is also known as the trigonal. This is missing all except P, and hexagonal also missing all except P. Okay, so thus we just count them as the 14 Bravais lattices, and here are the structures of the 14 Bravais lattices: simple cubic, body-centered cubic, face-centered cubic, and these two are abbreviated as BCC and FCC. And simple tetragonal, body-centered tetragonal. Simple orthorhombic, body-centered orthorhombic, base-centered orthorhombic, face-centered orthorhombic. Rhombohedral, they are not simple because all the others except simple are not available. So simply you can say at rhombohedral. Okay. Hexagonal, simple monoclinic, base-centered monoclinic, because there are 2 types of monoclinic. So that is why then you have to mention whether it is simple or base-centered. So simple monoclinic, base-centered monoclinic, and finally only one available, triclinic. Okay, so these are the 14 Bravais lattices. So that's all for today. Thank you.